Okay, so this week we on system charge. Oh my gosh, I broke it again. Dang it. There goes my big rich deck. Nothing a little glue and rubber bands can't hold it. I got an audience here with me today. I hope you ain't gonna be laughing back there the whole time, because right now you can't even breathe. All right, I'm gonna tape it together, but don't worry, because once I get this all together with glue and tape and rubber bands and stuff, maybe a couple of staples, I will be whacking my big rich, better watch what I say. I will be whacking this thing again against the desk, making sure. Whack! Yeah, get your attention, wake up! I already broke that in, now I broke that in. Man, if I was trying to go down a stream, huh? I'd be up the creek with a broken big wrist stick. Like a ninja. Ooh, wake up. Okay, so unit 10 goes like this. We're on system charging this week. Feel like slamming it down, but I don't know if someone might get stabbed or something. System charge, oh, we're in page 265 of your book. That's what you're supposed to be on, 265 in your book. System charging refers to adding refrigerant to the system. Now, the three next words are very important. And this is those three magical words. The correct charge, not just any charge, not the wrong charge, not a okay charge, might be charge. The correct charge is what? Added to the system, so they can operate effectively and efficiently. Write that down right now in your lecture notes. As it was designed to, and it's not always an easier task to accomplish. That's what you want, system charging. Now remember, this goes along with your EPA study stuff. Some refrigerants, namely single pound, may be added to the system in either vapor or liquid. Blended has to be in a liquid state. Blended has to be in a liquid state. You don't even know what that means. You want to know why you don't know what that means? Because I didn't tell you yet. But I will be telling you shortly. A scale should be used to determine how much freon's added to a system. The system's charge is evaluated by using superheat and subcooling calculations. That's the way we do it. I'll even show you the approach method this week. These factors include, or not limited to, you're going to use these factors to help you charge the system. High and low saturation pressures and temperatures, ambient temperatures, evaporation, superheat, condenser subcooling, compressor amperage draw, and temperature differentials across the heat exchange surfaces. Now, we'll tell you this. When we get to the lab in a couple weeks, you're going to be doing a lot of system charging. Some of you have already done it many, many, many times, okay? Until you're doing it in your sleep. At least you wake up thinking you was doing it in your sleep. Don't be attempting this while you're sleeping. It can be dangerous and a safety hazard. Now, as we read on page 267, we get to this section in your book that says vapor refrigerant charging. So before I move on, remember the correct charge, two words, correct charge must be added to operator's design. Added by weighing, measuring, and using operating pressures. Carefully monitor the evaporator superheat and these factors to correctly charge it. Now, let's see what your book says about vapor charging. This is accomplished by allowing vapor to flow out of the cylinder and into the system. When the pressure in the system is lower than that in the tank, then the refrigerant will leave the tank and go in the system. The system pressure has to be lower than the pressure in the, right? It's like the air in the balloon is stronger than the atmospheric pressure because it's being squeezed by the skin of the balloon. So when you let it go, the skin squeezes the air and pushes it back out into the atmosphere. Well, as long as the pressure is greater in your refrigerant tank than what's in the pressure, you can put the vapor in there. Now, this can be added to both. This is what you want to do. When the system is operating, refrigerant must be added to the low side of the system. So you can add it to both the low and high side if it's under a vacuum. But when it's operating, it must be on the low side of the system, because the low side system pressure is lower than the pressure in the tank. However, the high side of the system, the pressure is higher than the pressure in the tank. So it won't go in. Okay? If the tank is a one-trip tank, like a virgin refrigerant tank, it will not enter the tank. A one-trip is manufactured with a check valve. What is a check valve? A check valve means the refrigerant can only flow in one direction. When it tries to go backwards, the tank stops it from doing that. Okay, so it can't flow backwards. This happened for a reason. Way back in the days when we used to have refrigerant tanks, before we had recovery tanks, of course, we hooked our recovery machines back to our tank of Freon. Well, the tank of Freon wasn't built for that, and it'd get pretty hot. It'd get pretty full, and it'd get pretty hot. So what we did is we had to get recovery tanks, these yellow and gray tanks, that was able to handle the refrigerant coming back out of them. Now, a virgin tank of Freon has a check valve. That means like a color tank, like pink, green, blue, when you buy it at the orange, purple. When you buy these tanks at the supply house, those come with the check valves. You can put Freon back and forth with a recovery tank. Now look what it says. When you're putting refrigerant in a system, the tank loses pressure because you're letting the refrigerant out. And because it loses pressure, it's harder for it to come out. Let's say it's wintertime. It's been stuck in your truck all night. You take it out and you want to stick it in the low side of the system. It may not go in because the tank's so cold it lost pressure. It's at a lower pressure. You'll have to warm it. Whenever you, check this statement out, last paragraph 268 at the bottom. When the vapor refrigerant is pulled out of the cylinder, the vapor pressure is reduced and the liquid boils to replace it. If you ever had a can of paint or something and you kept painting it, you'd notice how cold that tank got. Because whenever temperature goes down, that's right, pressure goes down. Whenever pressure goes down, that's right, temperature goes down. So when you let something out of a tank, it gets cold. Same way with your refrigerant tank. Now what we do in the field, whenever it's safe and possible, we're charging the unit, we know the pressure's going down, so we sit it on top of the fan of the condensing unit and let the hot air keep it warm. There's also a way, your book says on 269, you sit it in a warm tub of water, and the water does not exceed 90 degrees. You can also put an electric blanket they make, a refrigerant tank blanket around it to warm it. Now this one's very important. Check this one out. Never take your torch and use it to heat the tank. Use gentle heat, 90-degree heat with warm water. Never use your torch. All right? Now, so this is vapor refrigerant. It can be added to the high and low side while it's not operating or under a vacuum. Vapor can be added to the low side while it is operating. I don't know why they always get that confused on the test, but you need to learn that because you'll be doing it in the field. The cylinder may need to be warmed to build up pressure to charge the system. Warm water can be used, never use a torch. Now, let's get to this part right here that's called, now if you watch your pictures in your book, it's pretty easy. They show you the pressure of the tank, and the pressure you gauge and how it can go in the system. All right, now liquid refrigerant charging. Let's talk about that. On page 269, this is normally accomplished in a liquid line. Liquid refrigerant goes in a liquid line. If the system's in a vacuum or it's evacuated, you can allow refrigerant straight into the liquid line. All right, now they will have a king valve stem like you see on picture 269. Let's see if they show that. Right here. So here's where your gauge port is, and this is going to the compressor. Notice this right here will allow refrigerant through, or if it pulls up, it won't let it through. If it goes all the way down, it stops it from going through the system. So let's define those three things right now on page 269. First one's backseated. This is the normal operating pressure of the valve. Refrigerant flows freely through the liquid line. So, when this valve is pulled all the way up, notice you don't get a gauge reading, but it's in normal operating. Liquid compressor and all right here is working fine. But notice this is closed off. That's called backseated. The next one's cracked off backseat. That means you take this stem at the top and start to turn it, and it comes off of this seat, and you can get a gauge reading. Mid-seated, like it is right here in this picture, means you can use your gauge to run a vacuum, charging, all that kind of stuff. And the last one's front-seated. When you screw the stem all the way down and this blocks this off, that means you've isolated that part of the system. You can pump down all the refrigerant into the condensing unit, and you've isolated it. So those are your four positions: back-seated, cracked off back seat, mid-seat, and front seat. Okay, any questions about that? Now remember this. Be careful not to overcharge your system. All right? Precautions must be taken when putting liquid in the suction line. Now remember this. You can't charge a system in the low side with liquid because you could damage the valves. However, with a blended refrigerant, let's say 410A, you have to charge a low side of system with a liquid. So you have to be careful that you don't get liquid back to your compressor valves because they can't compress liquid. You could damage them. So how do we do that? Check this out. There's a few different ways. Liquid must be vaporized into a gas when it enters the compressor, as damage can result in the compressor attempts to compress liquid. While working with blended, you have to let it leave as a liquid. Why? Because it's made of 2 or 3 different compounds. And for them to leave as a gas, the one with the smaller molecules will leave first. Now you have a fractionated and unequal blend going in the system. So if you turn it upside down, it leaves as a blended liquid. It won't fractionate, and you'll have the right blend going in the system. Now your book says, when you pour the liquid in there, the orifice, you can take a little deal called an orifice, like a quick check, and you quick charge, and you put that on your suction line, flip it, and it only allows 10 pounds of pressure of liquid to go into the suction line, which what? Vaporizes it, the low pressure, lowers the boiling point, and it quickly vaporizes into a gas entering the suction line. That's called a quick check charge. You could buy those. Now look what it says right here. You can use your manifold gauge on your low side, your compound low side, blue side of your manifold gauge, to slowly allow the liquid in through your valve in your manifold. Make sure you're not going over 10 pounds of pressure on your needle. You will do this in the lab. Almost every one of you's already done it, and you will do it. By cracking your gauge manifold a little bit, you're allowing that liquid in there to be flashed into a gas, and you can charge it like that through your manifold. It can act like a 10-pound pressure metering device, and it can vaporize before it goes in. The gauge manifold should be used only on compressors when the suction gas passes over the windings. If the lower portion of the compressor becomes cold, stop adding liquid. You're adding too much, and you can damage the compressor.